In this lesson, we focus on trigonometric identities. We will deal specifically with two identities, the quotient identity and the square identity. The quotient identity says that the tan of some angle theta is the same as the sine of theta over the cos of theta. So this is always true. So if I have the tan of 45, it will be the same as the sine of 45 over the cos of 45. If I have the tan of 30 degrees, it will be the same as the sine of 30 degrees over the cos of 30 degrees. So this is an identity, it's always true. The square identity says cos squared theta plus sine squared theta is always equals to 1. We can also write this square identity by taking the sine squared theta to the other side of the equation in this format. We'll have cos squared theta equals to 1 minus sine squared theta. Sine squared theta as well can be written as 1 minus cos squared theta. We can prove these two identities using the Cartesian plane. If we draw a Cartesian plane and some point which sits r units away from the origin, we remember that we can define the trigonometric ratios using this triangle. We know that the sine of theta will be given by y over r, which is the opposite over hypotenuse. The cos of theta will be given by x over r. The tan of theta will be given by y over x, which is opposite over adjacent. And we can also find the value of r by using the theorem of Pythagoras. We know Pythagoras says that the square of the hypotenuse is the sum of the squares of the other two sides. Now, to prove the quotient identity, to prove that tan theta equals to sine theta over cos theta, we can take the ratio sine theta over cos theta and write it in terms of x and y. It's sine theta over the cos of theta. So we write sine theta is y over r. We change this division to for simplicity's sake. And the cos of theta is x over r. Now we can write this, we can change this division sign into the multiplicative inverse, or into a multiplication by using the multiplicative inverse of this function. And r will cancel out. We will be left with y over x. But if you look at the definition of tan theta from the Cartesian plane, it's y over x. Therefore, the sine of theta over the cos of theta is y over x. Tan theta is y over x. Therefore, tan theta equals to sine theta over the cos of theta. Similarly, cos squared theta plus sine squared theta, we can write sine and cos in terms of x, y, and r. We know that cos theta is x over r, so we square that. Sine theta is y over r, and then we square that. We can simplify this, find the lowest common denominator, which is r squared. But we know the value for this one. X squared plus y squared is the same as r squared by Pythagoras. If you use the theorem of Pythagoras, they see that r squared is the same as x squared plus y squared. So we can write the numerator as r squared. It's r squared over r squared. They cancel out and you are left with 1. Now let us see how we actually apply this knowledge in the following problems. But before we start solving these problems, there are some hints that are very important and very useful in solving the identities, or solving trigonometric identities. So when you are given a trigonometric identity, your main task is to prove that one side of the identity equals to the other. So you choose one side, you simplify it using all your knowledge of trigonometry until it is the same as the other side. So you could pick the left hand side and make it look like the right hand side, or pick the right hand side and make it look like the left hand side. So what's important is to pick the most complicated side. You find that your identity as it is given, there is the side that looks more complicated. You pick the complicated side, change all the trigonometric functions into sine and cosine. And as you continue to simplify, you may find that it is necessary at some point to simplify the right hand side and the left hand side so that you arrive at the same answer in both on both sides. Sometimes you can multiply by 1 by using a suitable fraction, and then always remember to replace cos squared theta plus sin squared theta with 1 where it is necessary. You can also change 1 into cos squared theta plus sin squared theta, so they are interchangeable when you're working with trigonometric identities. And also remember that you can write 1 minus sin squared theta as cos squared theta, or 1 minus cos squared theta with sin squared theta. It comes from the square identity. Let us start with simplifying some trigonometric problems here, or expressions. In A, you are given tan squared theta x times cos squared x, and you are required to simplify this. Now, we know that tan can be expressed in terms of sine and cos. So we know that tan can be written as sine squared x over cos squared x. So it doesn't really matter. You know that the identity said tan theta equals to sine theta over cos theta. So if you find tan squared theta, you can write it as well as sine squared theta over cos squared theta. Now in this case, these two will cancel out, and you will only be left with sine squared x. When we come to the right hand to number B, we can do the same. We know that tan can be written in terms of sine and cos. Then we find the lowest common denominator, which is our cos squared x. And then the numerator becomes 1 minus sine squared x. But 1 minus sine squared x can be written as cos squared x. So we can have cos squared x over cos squared x, which gives us 1. Now let us prove an identity. This is our second example. We are required to prove the following identity. You are given sine x minus tan x times cos squared x divided by cos x minus 1 plus sine squared x equals to tan x. Remember, the idea is to pick one side and make sure that it looks like, the same as the other side. You could pick tan x, but this is very simple. It's already simplified, so it would be a challenge for you to turn tan x into this. So we normally pick the complicated side. In this case, our complicated side is the left hand side. So we abbreviate this to say left hand side. Now, this is our left hand side. We can now try to work out the left hand side until it looks exactly like the right hand side. Now, what do? We change everything that is not sine or cosine into sine and cosine. We have tan x there, we change it into sine x over cos x. In the denominator, we had minus 1. But we see that if we turn this minus 1 into cos squared x plus sine squared x, some terms here can cancel out. So we actually changed minus 1 into minus cos squared x plus sine squared x. If you further simplify in the numerator, I have cos squared x and then I have cos x at the bottom. So this will cancel the square. I'll be left. Okay. This cancels the square. I'll be left with only 1 cos x here. And in the denominator, I will have minus cos x minus sin x. So sin x and sin x will cancel out, so that I'm left with this cos x minus this cos x squared or this cos squared x. We can take out the common factor in the numerator. I have sin x and sin x over there. I can take it out and be left with 1 minus cos x. I can take out a common factor also in the denominator. I have cos x minus cos squared x, so I can take out cos x. After that, these two can cancel out. That and that cancels out, and I'm left with sin x over cos x. From the quotient identity, we know that sin x over cos x is the same as the tan of x. We have shown that this is equals to the right-hand side. Our right-hand side is tan x. Let's try yet another identity. In this example, we are required to prove the identity like in the previous example. The left-hand side is given by 1 over 1 plus sin theta plus 1 over 1 minus sin theta. And we are required to prove that this is the same as 2 tan theta over sin theta times cos theta. If you look at the right-hand side, it will be a challenge for us to take this and make it look like that. But we could try the left-hand side. The left-hand side is a fraction, so we are actually adding two fractions here. How would you add two numerical fractions? You find the lowest common denominator. To find the lowest common denominator for these two, I just simply multiply the two denominators. 1 plus sin theta times 1 minus sin theta, so I have that. Now I simplify. To simplify this, I say the denominator divided by this. These two will cancel out, and then I'm left with this. Then I write it down there. The denominator divided by that. These two cancels out. I'm left with this, and I write it down there. Minus sin theta plus sin theta, the two will cancel out. I'll be left with 1 plus 1, which is 2. If you expand the denominator, you are left with 1 minus sin squared theta. This is the difference of two squares. 1 minus sin squared theta is the same as cos squared theta. It is 1 minus sin squared theta. It could be written as cos squared theta using the square identity. So we could write 2 over cos squared theta. Now we managed to reduce this to one trigonometric ratio, but it is not equal to what we were asked to equate with. But remember that sometimes you may need to multiply or to simplify both sides in order to arrive at the desired solution. Now let's try to simplify the right-hand side. The right-hand side is given by 2 tan theta over sin theta times cos theta. Change tan theta into sine and cos. We can rewrite this division sign in the manner that will allow us to work with ease, this long division here. And now we can change this division sign into a multiplication by writing the multiplicative inverse of sin theta cos theta. In this case, sin theta and sin theta will cancel out. I'll be left with 2 times 1, which is 2, cos times cos, which is cos, 2 cos, cos squared theta. So this will be 2 over cos squared theta. But this is equals to the left-hand side. So we managed to prove that the right-hand side equals to the left-hand side. Let us prove yet another identity. In example 4, we are required to prove that 1 minus sin theta over 1 minus sin x over cos x is the same as cos x over 1 plus sin x. If you look at the left-hand side and the right-hand side, they are more or less the same. So you could pick any of the two sides to simplify this, but in this case, we are going to pick the left-hand side. But what would you do with this function in order to simplify it? Remember, we said you can multiply by 1 in the form of a suitable fraction in order to solve a problem. This is one of those problems where you need to multiply by 1 in order. So at the top here, if we can find something that can change this into the difference of two squares, and we know that you can see that if we multiply by 1 plus sine x, we can actually get the difference of two squares in the numerator. So that fraction, or that one that we're talking about here, or that suitable fraction, will be 1 plus sine x, 1 plus sine x, because we are interested in changing this into 1 minus sine squared theta. So if we multiply these two, we end up with 1 minus sine squared theta all over cos theta into 1 plus sine theta. But we know that 1 minus sine squared theta is the same as cos squared theta. So we can write that as cos squared theta. Now we can cancel the square there and cancel out the cos x in the denominator. You'll be left with cos x over 1 plus sine x, which is equals to the right hand side. So we're able to prove that the left hand side is equal to the right hand side, or left hand side equals to the right hand side. Let us prove yet another identity here. In this one, you have to show that the left hand side equals to the right hand side. In other words, this is a simpler one because we've already dealt with a reduction formula in one of the videos that we did for this trigonometric series. Now, we are going to use the reduction formula to simplify this until it looks like sine x. Like we said, you pick the most complicated side and make sure that it looks like the other simpler side. We would have a bigger challenge if we had to turn sine into this. Now we pick the left hand side and use the reduction formula. Remember, this is in the second quadrant, sine is positive. This is in the first quadrant, tan is positive. This is in the first quadrant, cos is positive, and it changes to its cofunction. So we can actually write it down, and you always have to put the restrictions. The denominator to this problem cannot be 0, because if it's 0, division by 0 is undefined. So you always put the restrictions there and show that the denominator cannot be 0. Now we said 180 degrees minus x. This is in the second quadrant. In the second quadrant, sine is positive, so we can reduce this to just the sine of x. This is in the first quadrant, tan is positive. We can simply reduce this to the tan of x. That is just cos x. This we can reduce to the cos of x using cofunctions. Remember, in 90 degrees plus minus theta, cos changes to its cofunction, which is sine. And this is in the first quadrant, cos is positive, so we're going to have sine, positive sine x. Now we change cos into sine and cos. We change tan x into sine and cos. Cos and cos will cancel out. And sine will cancel out. And finally, you are left with the sine of x, which is equals to the right hand side. So you are required to reduce this until it looks like sine x. Now there's one problem which requires your understanding of cofunctions together with the square identity that we have just worked with here and also proved. The square identity, the cos squared theta plus sine squared theta equals to 1. Now you have been given a problem. They say simplify without using a calculator. You are given a summation problem. Starting from a equals to 38 to a equals to 52 of cos squared a. Remember, this simply means you have to sum each cos squared of a as a increases. So it will be cos squared 38, cos squared 39, cos squared 40, cos squared up until you arrive at 50. We can write it down like this. and so until we arrive at cos squared 52. So it's cos squared 38, cos squared 39, all the way up until cos squared 52. Having it in this manner doesn't really help because there's nothing we can do. So the best way is to remember the core functions. We know that sine and cosine are core functions of each other. So if we write this in reverse, if you look at this, the sine of 52, I mean the cos squared 52 will be the same as sine squared 38 degrees. If you add 38 and 52, they give you 90. Cos squared 51 degrees is the same as sine squared 39. The two add up to 90 degrees. So we could do the same all the way up until 45, and we have nothing more to do. So if you look here, we've actually reversed up until 44. So we have this one and that one, this and that, this and that, this and that. We can actually sum them up. We can sum them up in this manner, that cos squared 38 degrees plus sine squared 38 degrees, we know that this is equals to 1. We can do this for all the 1, 2, 3, 4, 5, 6, 7. It will be 7 there and then 7 here. We could do that, and the only one that will be left without a pair is cos squared 45. So we could go on do that 7 times until we are left with just 7 times 1. Remember, cos squared 38 degrees plus sine squared 38 degrees by the square identity is equals to 1. So we have 7 times 1 plus the 45 degrees, cos squared 45 degrees that is left alone there. So this is simply 1 over the square root of 2 squared, which gives us 1 over 2. This is 7.5.